Hello, hello, hello. Cool. Say hello in the chat if you are here. Just double check Twitter. Cool, the tweet is there. Yep, say hello. Let me know how the audio is. If you can hear me all right. We've got a couple of people in there, which is cool. Yeah, stream looks good. Hopefully the audio is good. Let's double check OBS. Yeah, all good by the looks of it. Cool. Right. So this is probably going to be an hour long, an hour or so. We'll be following on from the last stream. If you didn't catch it, you can go back and watch it. It's on my channel. I basically started implementing an interpreter in Rust. So for just a small sort of toy scripting language, just playing around with Rust, having some fun. So we're going to carry on with that. So last time, you can kind of see it here on GitHub. Last time I started working on the lexer, so taking a stream of input and passing out into tokens. So an example might be here. We turn the letters LET into a token let or a let token. Foo would be an identifier, this would be an assign, and then this would be a number. Since then, I've done a little bit of refactoring. So I've moved everything out into individual files. So we now have a file for the tokens. So we've got this token struct, and we've got this token enum, token kind enum up here. So token kind is each type of token in the language, and the token struct is what stores the kind and the literal, which is the the string representation of a token. So let would be let and so on. So that's now in its own file. We've also got lexer, which is kind of what I've rewritten basically. So it's very similar to before. We've got a vector, which is similar to an array or a collection, and it's just a collection of chars, which are single characters in Rust. And we've also got two sort of increment counters. We've got current and next, so this determines where we currently are in the stream, and the next one is where we'll look to next. So this would let you peek ahead without consuming a token. And then we're also storing the current character in this jar field. If you're not familiar with Rust and this is like your first time seeing it, you might want to go back and watch the other stream. I explain a couple of the basic things that I'm using, like structs and the impl keyword and how methods work on structs. So a couple of other things. The new method now takes in the input. It initializes the new state on the struct. And we're also filling in the first char, so we don't have to start on this like null character. We've got a couple of other convenience methods. So we've got the read method. This is going to advance the, this should be escaped. This is going to advance the current pointer by 1, basically just setting it to next, which should always be 1 ahead, and then we'll set the next to the current +1. Or you could, plus equals 1 there, but this is a bit more verbose for now. It could be changed later. We're making sure that if you're going too far ahead, so if the next is actually greater than the length, we just put the null character in there, and otherwise we pluck the character out of the source and fill it into char. So the char field on the struct is just so that we don't have to keep on calling self.currentChar as a method like we were before, which you can kind of see down here. We were calling self.currentChar in a lot of places, and it was kind of bad. you know, calling the same method and digging into the vector, doing index lookups and unwrapping and stuff like that. So now we're just straight up doing an index search on the source and assigning it to the char. We've got people in there? Yeah, cool. A couple of other methods. We've got this function called skip whitespace. This can actually be removed, we don't need this. And this is basically going to go through each of the characters, and if it's whitespace, it's going to read and skip over that. Whitespace doesn't actually matter in this language. It's not like Python where we're depending on indentation and dedentation. So in theory, once we've read the let keyword, we can completely skip over all of these spaces, which would kind of let you do something like this. So this would still be a single statement. It would skip over all this white space and look for the next token. And then we've got another impl here. So we're going to be implementing the Iterator Trait. In Rust, you can kind of think as traits as interfaces in PHP, if you're a PHP dev. So this has some method definition on it. We can click through here. We can see that it's expecting a next function to be defined on the structure that we're implementing it for. We've got a type declaration up here. This is how Rust gets around the whole variance sort of thing. So iterator will use type item internally in its type definition or in its function definition. So you can see we're returning an optional item, but we're not going to be calling it item, so instead we can declare the type and return our own type down here, and Rust won't care about it. The compiler won't have a go at us for it. And the next method is very simple. It just returns an option token. If we're beyond the length of the source, we return none, which is basically like null. We skip over any white space because we don't really care about white space. And then this is where all the heavy lifting goes. This could be moved out later on. But for now, we're saying match against the self.char, so match against the current character. If it's an equals, we return a particular kind of token. If it's alphabetic, we build up an identifier, or we check against some list of keywords. So we've only got let as a keyword at the minute. If it's numeric, we continue going until we find something that's no longer numeric. And we also support number separators. So you can use underscore. You can see that here. This is the same as 100,000. This is just a way of reading it a bit nicely. And if it is that, we just skip over it. If it's not a numeric number and it's not a period, then we break out of the loop, because this means that we're no longer looking at a number. So if it's white space or a letter, something like that, it will break and it will finish reading the number. Otherwise, we push it and we keep the periods in there, because the idea is that a bit like JavaScript only has the number type. It has a like big int and stuff like that, but a number is both an int and a float. So we're going to follow that same pattern where all integers are stored as 64-bit floating point numbers, meaning if we've got 10, we'll actually be storing that as 10.0. So yeah, this is kind of it. We've got an unimplemented macro here. So if for whatever reason we had a token, let's just say bang, we'll put a bang in the middle, and we run this, it's going to have a go at us because we've not actually implemented this yet. And this is great for debugging. And that comes out of the box with Rust. So we can just call this and it will panic for us. We'll read past the character that we're matching against. So that'll skip over self.char. And yeah, that's basically it. I'm not sure if this would cause problems, to be honest. Like here, if we had this close together, is this going to cause an issue? Yeah, it does cause an issue. So maybe we'll get rid of that. And up here instead, because if if I get rid of that, that should, yeah, that should get into an infinite loop. So we need to put the read up here instead. Perfect. So yeah, it's taken this stream of input. We'll put the white space back in there so it's a bit more readable. It's taken this input and it's given us a let token, an identifier, an assign, and a number. And you can see we've removed the number separators to make it easier to pass them into floating point numbers. And yeah, we're going to go ahead with this. In the first stream, I added support for strings, but we'll come back to this later because I want the strings to be solid. We didn't really accept any escapes or anything like that. So we will do something simpler for now, just once we get the parser in place. And we have got people here. We've got one person here. Say hello if you are here. I'm not expecting many people to watch this, to be completely honest. It's nearly 9 o'clock on a Sunday in the UK. It's a bank holiday tomorrow, so most people are going to be off work, probably down the pub. So I'm not imagining we're going to have a huge crowd. We had quite a few people watch the last one, but people come back and watch them afterwards anyway. But I'm just going to work. It gives me an excuse to work on something that is fun and experimental. Cool. So we're going to stick with this for now, I think. We're going to stick with this. We're going to use this as our test case for building the parser. And if you don't know what a parser is, so at the minute we've got like a token layer, a token identifier, a T, assign. I can't type, really can't type. And then we've got a T number. And the idea behind the parser is we're going to look at this stream of tokens now instead of a stream of characters. We're going to look at this stream of tokens and turn this into something like a let statement. So when we hit the word let or the token let, we're going to know that we're declaring a new variable. So we're going to open up a let statement and we want to know what the identifier is, and that will become the T ident. And then we also want the sort of the initial value, which will be everything after T assign. And this is an expression. So this is valid JavaScript. So this would be the name of the variable. Everything after the equals would be the expression. So let's get started. Also, this is how you work with modules in Rust. If you're building an app or a package, you have modules, and in your main.rs you use the mod keyword, and this makes them available to the rest of your app. So you can see in the Lexa, crate is referring to the top level here. So it's saying crate, looking at main. Any modules that we've exposed up here will be available via their namespace, so token Lexa, or whatever you've declared them as here, basically. Cool, so I'm actually going to commit this to Git real quick. We'll say refactor Lexa logic, sign that commit, and we'll push back. Perfect. Another thing that's worth noting, previously on the first stream, this lex method would go through the entire input, figure out if there were any tokens, build up a vector of tokens, and then return those tokens. That's fine for debugging, which is what we're doing inside of main. We're saying while there is some token being returned by next, we're just printing out that token. But for performance reasons, you don't want to lex an entire file or tokenize an entire file. You'd probably want to do that lazily. So let the parser do that. Because if you hit any errors, then you're going to stop lexing. You're going to stop the tokenization process and exit early. very early optimization, but it's one worth making, because as we flesh this out, we don't want to go back later to do all of this. So I think another thing that I'm going to need is a peak method. So the next method will advance the counter by 1. So it uses self.next, but it uses self.char. So it says if the next one is going to be greater than the current one, we don't want to do anything. I think this is fine. I think this is fine for now. If anything, we want to move out this match logic. Because what we will want is a peak method, which will be similar to next, but it's not going to advance the internal counter. But it's kind of problematic because this read method is also mutating the internal counter. We'll see how far we can get with next. It'll just be a case of advancing the counter instead of checking it against something that might be coming up. So let's close that. And let's create a new file called parser. I'm actually going to open OBS because last time I realized that the code that was on the right hand side of the screen was kind of hidden by my face. So where shall I put my face? I'll leave my face here for now. That's fine. We'll leave it here. So first things first, we'll go in here and we'll declare the mod, the module. And let's create a struct. Now this needs to be public because we want to access this inside of main. We're going to implement the parser as well. And the parser will store the lexer. So up here we can import the lexer. And we can declare the type of this here. And we can also create a constructor. So we'll use the new method. We will say we're going to receive a lexer. And we're going to return self with that lexer. Perfect. So if I go into main.rs and I open up, we'll get rid of this for now. We don't need this to be mutable, I don't think, but we'll let p equal parser new, and we'll just pass in lex. Perfect. So this is now going to be out of scope, so we can't technically use this past here because of Rust. Rust will have a go at us. But if I compile this, it should be quite happy. We've not made any issues. Perfect. It's giving us warnings because we're not reading any of this data, but we will be. Cool. So we actually want to pass the entire program out because we need to have an entire AST before we can read it, an abstract syntax tree, which is going to be like a tree of nodes where each branch is a new node. So I think what we can do is we'll have a public function called parse, and this needs a mutable reference to self because we're going to be mutating the state of Lexa up here. Perfect. Let's also create another struct inside of here called program, and this is going to hold our AST. And parse is going to return a program. And first things first, we're not actually returning a program. So let's say let p equal program, and we'll return p. And this is going to have a go at us because we're declaring a public method, but we're exposing a private type. This struct isn't public, so we'll put a pub on there, and this method is never called. So let's just go down here. We'll say let program equal p.parse. And because we're using a mutable reference inside of the parser, we need to make this a mutable binding as well. And this seems to work fine. Perfect. Now, program doesn't actually need to be a struct that has fields. Instead, it can kind of act as a type. So let's use pub type instead, and we'll call this program. And program is also going to be a vector, and it's going to hold a bunch of statements. We haven't declared statements yet, but we can do this. We create a new AST module. So this is where we're going to define all of our AST statements, all of our nodes, and we'll put this as a mod. And we will have probably an enum for these statements. So we'll create a public enum, and we'll put some derivations on there. So we'll put debug on there, which will do some pretty printing for us. And we also need to import the statement enum. Perfect. So let's create a vector. Let's create a vector of statements, and this will be vec statement new, and we can just return statements. And now this is happy because program is just a type alias for a vector of statements, and that's exactly what we're returning. So if we run again, we don't get any issues. We will set up some better sort of static analysis later. Rust has something called Clippy, which is good for giving you hints on how to make your code more rusty, more idiomatic. Perfect. So let's start parsing some statements. Let's put a quick line in here, and we'll print out the program. This will be empty for now. It will look like an empty array, but we will put something in there at some point. Okay, so we're going to start with a let statement. So let's call this let. And the unique thing in Rust, that is not what I wanted to do. Where has VS Code gone? Not there, not there. Let's open this up again. Perfect, there you go. So the unique thing in Rust is you can actually store, you can have fields in your enums. So if we create a new file here, in PHP 8.1 anyway, there will be enums, and you'll be able to say something like enum statement, but the cases won't be able to store any variables, right? They'll purely be sort of decorative. You can type hint this and pass through statement let, but you won't be able to store any variables. That is something that is being worked on in the background, or it will be proposed as an RFC at some point, but it's not in the current enum implementation. I believe Larry Garfield has a work in progress RFC, or draft RFC for that. But that will implement fields or state held within an enum. So in Rust, we can create these struct-like enums. So for a let statement, we have the name of the variable. In here it'll be foo, and we also have the initial value, which will be the expression on the right-hand side. That is optional, actually. You would be able to come in here and just say let foo like you can in PHP and in JavaScript, sorry, and initialize it without any value. That is something we will support, but for now we'll expect an expression. we won't allow that for now. So let's call this, what do we want to call this? Names don't matter, we'll call it init. And init is going to be an expression of some sort, and this type isn't defined yet. It will be soon, but it's not right now. So let's have a think. I'm guessing expression can also be an enum. We'll put it all in the same file for now. We can refactor later. So we're going to need to add this debug as well. So this will stop having a go at us. And expression, there'll be a couple of types of expression, of course. But for now, we can just go ahead with the parsing. I guess we can sort this out later. We want to create this let statement at some point. So similar to what we did before, we'll say while let sum t equals self dot lexer dot next. So this is saying while lexer dot next returns some kind of token, as long as it doesn't return none, this loop will keep on running. And we'll call this token. Now we want to match against this token, so we can match against this token. And now it's going to have a go at us because we're not covering all of the cases that token can have. You know, there's all of the types inside a token. And we're going to take real advantage of the pattern matching that Rust provides here. Although, do we need to? We can probably just match against token.kind. This will be a lot simpler. So we'll start with token. It would help if I imported it. So we'll use that. We'll use token kind. And we'll say if we come across token kind let, we want to drop into this block. Otherwise we'll say that, sorry, we've not implemented it yet. Great. So if we just panic or print line here, and we just print out the token, if we run this, you can see it's reaching that function, and we're able to access this token here. Great. So now that we know we've got a let token, we can advance over that and we can get the identifier. So we'll say let identifier, let identifier equals self.lexer.next. So we've skipped over the let token and we're going to move on to the next one, which in our case is foo. And if we print line on identifier, we should see a token identifier, some token identifier, because self.lexer.next can return none. So instead we'll say if let sum t or identifier equals self.lexer.next, we will just return identifier. Otherwise we're going to panic and we're going to say we expected an identifier. We've not got any line information or anything like that yet. It's very rough. A good way of testing this is just to remove this and just put a let. You can see it's having a go at us because we've not put in an identifier. If we put let foo, it's not going to have a go at us. It's empty because we're not pushing anything back to the vector quite yet. So let's do this. Great. So now if we print line the identifier, this is also going to be a token. Yep. And we've got the literal value, which is perfect. We're going to, what we're going to do, we're going to consume, we need to skip over the equal sign. So if let sum, this is kind of where the peak method would come in really handy actually. Let's implement the peak method in the Lexa. Should be relatively simple. So we'll go up here and, or can we actually say self.lexa.peakable? Does this actually work? Move occurs which does not implement the copy trait. Right, okay, that's fine. We won't do this. We'll implement the method ourselves. So we'll have a public function called peak. This is going to return an option token as well. Let's just scroll down here. The implementation is basically going to be exactly the same as next, except we're not going to move over the current counter. So we'll say let char equals self.char, and we'll take in a reference to self. Or we'll check first if self.next is greater than or equal to the length of our string, meaning we're at the very end. We can return early, just return none. We can skip white space. And we can also say we want to store the current character so that we can restore state. Do we want to do this before? Do we want to do this before we skip the white space? Probably. Yeah. And we can I guess next is kind of misleading as a method name because it's matching against the current character instead of the next character. I think that's fine because we're saying we want to consume that token. We want to, eat up all the characters for that token. So we'll let char equals self.char. Next, so this is going to hold the current char. We probably want to say let self.char, or sorry, not let self.char. We need this to be mutable because we're about to modify the state. Self.char can equal self.source self.next. So this is going to pull out the next char, and then we want to match token. This is going to be a new method, and then we can set this back to what it was before, and also store the current. Old current equals self.current. Old next equals self.next. Old char equals that because we're setting inside a new char. We're going to match the token. We're going to set this to old char. Self.current equals old current. Self.next equals old next. The match token is going to do all the white space handling, and we'll say let t equal this, and we'll return some t. Let's call this token just to be super clear about what's what. So this match token method doesn't actually exist yet, so we'll put this inside of here. Match token. This is going to be a mutable reference to self, and we will return a token. And now we just want to take all of this, put it in here, and return the value of match, so we can get rid of the variable declaration, binding, return that, and down here we can let token equal self dot match token and just return token. So does this compile? It does, but it's saying that something is not implemented on line 27. A parser. Actually, it's telling us something's not implemented inside of parser, which in our case is going to be the equals sign. Cool. So I think we're all good in terms of this little refactor. So assign if let some token kind token kind assign. I'll explain this in just a second. Equal self.lexer.peak. What can we say if not let? No, that doesn't matter. I think we need to say if not matches. So this is a macro here. It takes in an expression and a range of patterns, and it matches against the expression and those patterns. So we can say if self.lexer.peak doesn't match some token, I need to pull in token. I really need to learn like the keyboard shortcuts for Rust. I'm sure there's some magic stuff that it can do. So this is a bit confusing. If you don't really understand Rust, have we got anyone watching? We've got one person here. Nice. Yeah, so this probably won't make sense at first, but instead of having to implement the match for us, it's going to expand out. So we're going to say if this value does not match this pattern, and this pattern is saying it must be some, so it can't be none. It must be a token struct, and its kind field must match this value. So it recursively goes through. Is it some? If yes, it carries on. Is it token? It carries on and it looks at the field. Is the kind equal to token kind assign? If it is, it returns true, so we never fall inside of this block. If it's not, then we want to return early because we've not got anything in place. But in our case, we actually don't yet, because remember we're not allowing expressions to be forgotten about. We're expecting an expression, so we can panic and we can say expected token, or expected and equal for assignment. And we can check if this is working by simply doing this, running it. And it panicked. It says panicked, expected an equal sign for assignment. So we're all good. Let's put this back. And now if we run it again, it won't panic. But we need to consume this because it's going to fall down into here for the assign. So we'll say self.lexer.next just to gobble up that. And this will still have a go at us. But if everything is working, we should be able to print line on the token. Yeah, there we go. So we can print line on the token. And because the peak isn't actually advancing it, when we come down here and say self.lexer.next, the next token is going to be the number. So it falls down into here because we haven't got a condition for it. Perfect. Let's go back into unimplemented. Great. So we've got let statements being passed. We're not actually doing anything with the identifier right now, but we will do soon. Now we need to parse out the expression. So we'll say self.parse expression. This is a new method that we're going to add on to the parser, and it's going to be responsible for looking at everything that can be an expression. So let's create this. I don't know if it needs to be public yet. We definitely need a mutable reference, and this is going to return an expression. So let's pull this in up here. Expression is not public yet, is it? Yes, it is. Perfect. This is going to return an expression. But what sort of expression is it going to return? Because we need to we need to loop and keep on looping. So I guess we can, for now, just match against numbers. I think that'll work. If we get all of the basic architecture in place for an interpreter, and then we expand on it later and refactor. So, what type of expressions have you got? In JavaScript, you've got literal expressions. So this would be a number literal. If you had a string like hi, this is a string literal. JavaScript has some stuff like object literals. You have array literals as well. So we'll create one called number. And what do we want to store in this number? Let's think. If we've got a number expression, we probably want to store the number itself. So like I showed you up here with these named values on the enum, we can actually do the same thing shorthand where we don't give everything a name. Instead, we just give it a type. So this number is going to store some sort of 64-bit floating point number. And now inside of here, we can match self.lexa.next. We've not covered all the patterns, which is fine. This is really naive because we've not got any like binding power. So we've got no like precedence. If you were to do +1 × 2, you'd want this to be evaluated first, like that, because of the precedence of the multiplication. You want to do 2 × 2 and then add that on to this big number. We've not got anything like that yet, but we will get there. So for now, we're going to match self.lexa.next. And I think we can... No, we can't unwrap this because it might return none. So instead, we'll have to match against the sum option. We'll say match against a token, and the token kind will be a number, and we don't care about the fields. We can just spread those out and say let them be whatever. Let's also add an unimplemented block for now, and we need to return an expression. So let's just do an expression number, and we actually want the literal as well here. Which is fine because I think this will basically give us the literal value, and we can say literal.parse. Does this work? Mismatch types expected, F64 found enum result. So we need to unwrap this. And now this should work. If we print line on the expression, it should be an expression number, which it is, and it's been passed into a floating point number correctly. So up here, we can change this into an integer, and it still works, but you can see it's got the trailing 0, like the decimal place. Let's try it with more decimal places. They all get stored correctly. Perfect. So we'll go back into this state for now. So we're parsing out expressions very naively. We're only supporting number literals at the moment, but this is fine for now because it's the general concept of the AST. Let's get rid of that print line. And now we can just return the statement. We can push to this statements variable. So we can say statements.push, make it mutable using mut. We can statements.push a new statement, and it will be a let statement, and the fields are going to be name, which is the identifier.literal, and the what did I call it again? Init. What have I done? What have I done? Let's just go back into here. Cool. Let's change this initial to, we'll call it initial instead. And this will be equal to the expression. So now, when we run this, we end up with an array. Let me just zoom in a little bit here. We end up with a let statement with the name of foo, and the initial value is just a number literal, which is perfect. Exactly what we want. So let's commit this. We'll say whip basic parser. Do I need to zoom out again? Reload. Basic parser. Okay, it's having a go at me. This is GPG. Being a real pain in the ass. Whip basic parser. There we go. That's more like it. Perfect. So yeah, this is the most basic parser we could write with what we've done so far. How long have I been streaming for? Where does it say? Where does it say? Where does it say? Nearly an hour. 50 minutes. Let's do another 10 minutes. Let's start supporting some more parser rules. Let's flesh out the expression stuff so that we can do more complex expressions like prefix operations and multiplication, that sort of stuff. Yeah, where do we begin? So when you think of an expression, normally they have like a left-hand side and a right-hand side. So in the case of 100 plus 200, this is your left-hand side of the expression. This could be anything you want. You could have a bracket, a function call, anything. And then you have the plus, which is an infix operator. It sits between two expressions and it does some operation. And then you have the right-hand side as well. You do also have just the left-hand side with no infix operator. And then you have prefix operators or unary operators like a bang or a minus, which negates the value, or a tilde in JavaScript. So you have the concept of binding power. And now binding power kind of determines how strong a particular operator is against another, and it determines what order things should be executed in, like precedence. This has a higher binding power to the left-hand side or to the right-hand side. So let's simplify, not simplify. We don't want to simplify anything. We want to make it more complex. Parse expression needs to accept a binding power. So let's call this BP, and it can just be an unsigned integer for now. And we're going to start by matching the left-hand side, obviously. This is the left-hand side of the expression, but we have no infix and no right-hand side. So let's call this LHS for left-hand side. Perfect. And we'll also just return LHS for now. LHS. So we've got the left-hand side. That's fine. So that could be a string. It could be a number. We'll leave the unimplemented there for now. And now what we want to say is we want to keep on passing the expressions until something changes. So we'll use an infinite loop, just to be rusty. We won't say while true or while some condition, we'll just use an infinite loop. We want to get the let's think. We want to get the next token, because it might be like an operator, like a multiplication. So we'll say let op, or let infix, I guess. Let infix equal, this is having a go at us up here because we're not passing through a binding power. We'll just pass through 0 for now. Self.lexer.peak. And now this is going to be the next token if it exists. If it doesn't exist, we'll do this if statement situation thing. So if it does return some token, we can return the infix, otherwise we can break and exit the loop early, and the left hand side will just be returned as it is. Perfect. Now we need to provide this operator with some sort of binding power. So we need to have a place to get the binding powers for these operators. Let's think. We don't actually need the, we'll let this, we'll say let literal equal infix op. This isn't a public, sorry, not infix op, infix literal. We don't really care about the type right now. We just care about what the literal is. We're going to match it against like a binary operator or something like that. Or do we? I think I'm getting ahead of myself. So let's pass out the infix. Once we've got the infix, we need to get the binding power for that operator. So let's just do infix binding power, and we're gonna pass it the token type and return a usize. I think that should be fine. We can return a usize or a U8. Yeah, a U8 works, an 8-bit integer. We've already imported token kind, so that's fine. We can let the binding power equal match the kind. And what types do we have here? Let's think. So these aren't even postfix operators, are they? These are infix operators. So I was thinking of like plus and stuff like that, but we're not worrying about that. We're simply worrying about things in between two expressions. So let's say we can match the kind. We can say if it is a plus, so we're going to need some more tokens. So we'll go into our token kind. We'll say plus, and let's do multiply as well. And let's go in here and we'll say 1 plus 2 times 4. So what we would expect this to be is 2 times 4 plus 1, which is 9. But if without the binding power, it might say, well, we've got a 1, we've got a plus and a 2. So this is 3, times it by 4 is 12. But we want it to use those proper maths rules. So we'll use this new expression. And we also need to make sure we're getting these tokens come in. So further down here, we can say if it is a plus sign, we can read the plus sign, and we'll create a new token with the kind of plus, and the literal can just be plus to owned, And similar to the plus, we can have the asterisk, or we're calling it multiply in this case. Token kind multiply, and the literal is going to be the asterisk to owned. Perfect. So now we're passing out these tokens, which is great. These will already be handled because they're numbers. Okay, so if we can match the kind against a token kind of plus, we can return what should we say? A high number, 99, which is too big. 16. We can return that directly, can't we? Yes. No? We'll make this an option. And because this is infix, we need a left-hand binding power and a right-hand binding power. So we'll use a tuple. So we'll return 16 if we'll just do this. If it's any other of the kinds, we'll just return none. And I'm jumping about all over the place. And we'll return some binding power. And here we can say 6 and 7. So the right hand side has a greater binding power than the left hand side, which means that the right hand side should be evaluated first. Yeah, I think that's right. We need to return that. We don't need to assign it to BP. Okay, and we'll do token kind multiply as well. Now multiply is probably going to have higher precedence than plus. So we might actually want to, or greater binding power. Precedence is the same sort of thing. So let's go 8 and 9. 6, 7, 8, 9. I've started higher because there's going to be things that are lower down there. So this gives us some breathing room. Cool. So inside of the loop now, we need to get the binding power. Yeah, we need to get the binding power, but we could be returning none. So we'll have to use if let sum, and then we've got a tuple. So we've got the LBP and the right BP equal infix binding power for the infix kind. So again, we need to pass through the token kind, not the token itself. And this is going to pluck out the left binding power and the right binding power. If the left binding power is less than this binding power, we want to break. Why is this? Expected U8 found U size. Okay, let's just change this to U8 for simplicity's sake. If the left binding power is less than the minimum binding power, which we've specified, then we want to break because it shouldn't have precedence. We don't need to run that operation. We can get the next operator, I guess. So next op. Yeah, I think that works. Which will be next. And we'll just unwrap this for now. We can add in error handling later. We want to get the the right hand side, so we can get the right hand side, and this is going to be passing the expression again, but we're going to be passing through the right hand side's binding power, which we're pulling through here. There's a bit of recursion going on, which is why tree walk and AST stuff is generally slower than like PHP, which has bytecode and JavaScript, which is JIT compiled. And now we want to turn the left-hand side into an infix expression. So we need to provide the left-hand side, the operator, and the right-hand side. So left-hand side needs to be mutable, I guess. Yeah, so we'll say let mut. So left-hand side is now going to be, what should we call this? Should we just do another function? Yep, make infix expression. We'll give it the left-hand side. We'll give it the operator, or the next operator, and we'll give it the right-hand side. Let's go down here and implement this function. So make infix expression. We've got the left-hand side, which is an expression. We've got the operator, which is a token. We've got the right-hand side, which is also an expression. We're going to be returning an expression, I suppose. Will we return an expression? Yes. I think we need to get the kind out of this though. I think this needs to be. We can call it op. We'll pass through the op and go down here and we'll change this to token kind. We don't care about the literal or anything like that. We can match against the kind if we need that. So yeah, I think this is right. We're going to match against the operator, and based on what the operator is, we're going to return a certain type of expression. So for the expressions, we need a couple more here because we've got binary expressions. So let's do binary expression. We're going to have an expression on the left. We're going to need to wrap this in a box so that we don't have, I'll show you what the error would say if we were to put an expression into here. It has an infinite size because we're using an expression inside of an expression, so we can't determine a fixed size for this. So if we wrap it in a box, it gets happy with us. And if we read what a box does, it assists with heap allocation. So Rust does a lot of the memory stuff for us. I think we want another enum as well for binary ops. So we'll have a plus and we'll have a multiply. And we'll put some debug stuff in there. Because now we can separate this from our token types completely. And we can use that instead. Okay, so a binary op will have a left-hand side, it will have some sort of operation, and it will also have a right-hand side, which will also be an expression. And these expressions could be more binary operations. In our case, they will be, because we'll have 1 plus 2 times 4, so we'll have that on the right-hand side, that on the left-hand side, and then that as the operator. Or as the binary op. So let's match against the operator. We'll say if it's token kind plus, we'll return an expression, binary, with the left-hand side, which needs to be boxes. So we'll redeclare that, and we'll wrap the left-hand side in a box. Let's also do the binary op. So we need to pull binary op in up here. So this is going to be a plus, and we've also got the right hand side. Let's also cover that multiply. So a similar thing, we've got the left hand side, we've got the multiply binary op and the right hand side, and we can leave the rest unimplemented for now. Cool. So up here we've got the left hand side, we're making an infix expression from the left hand side, the operator, and the right hand side. Great. So now, back up here, we're reassigning the left-hand side. so that's going to be updating this. So once we've updated the left-hand side, we can continue the loop. So the left-hand side is going to be the latest. It's going to go back up to the top, get the next token. We're peaking, otherwise we want to break. We want to consume that token down here somewhere. Actually, no, we don't, because that's what this is doing down here. We're peaking up here. If it's none, we break and we don't update the lexer because it will be handled somewhere else. If we have some sort of binding power from that operator, from the infix operator, then we're skipping over it and retrieving the operator anyway. So if there's no binding power for the infix, do we just want to break out of the loop and just return the left-hand side as it is? Potentially, that could work. Let's compile it and see what it says. Let's hide this as well. Okay, I think this has worked. So we've made pretty good progress actually in an hour. So we've got a let statement with the name of foo, and the initial value is going to be equal to a binary operation where on the left hand side we have the number 1, and we're adding the result of this expression here, which is a binary operation or a binary expression where we're multiplying 2 by 4, and then we get the value back out basically and assign it to foo. So this seems to be working. Why don't we then, before we finish, let's zoom back out. Before we finish, why don't we add support for minus and divide as well? So let's go back into our lexer. Here we'll say if it's that, we can read the character. We'll create a new token, and the token kind will be subtract, and the literal will be minus toString. We need to return that value and implement subtract. Great. Let's also do divide. We'll copy this, change this to that, do divide, and then in here we can do that as well. So now we can tokenize all of those. In our parser, we're passing an expression. Down here we need to add in the cases for subtract and also divide. So what is the binding power for subtract and divide? What is the binding power? So I think plus and minus have the same binding power because divide and multiply have higher binding powers. So we can flatten this out into something like this. So if the kind is plus, or if it's subtract, it will return this. And can multiply and divide have the same ones? Yes. That's fine. So they have the same binding power. So let's think of something that we can easily verify. So if we've got 1 plus 2 minus 3, that's going to be 0. And then we'd expect it to times by 4 and then divide by 5. If we run this, it's not implemented in parser. Did I miss something off? Line 100? Yes, I did. I need to implement the expressions for those. So we'll have a binary expression. We'll have a binary op called divide. We'll add that in a second. And we'll also have a subtract, which will be a binary op. And this will be subtract. And then it'll be the right hand side. let's add these binary ops in. Divide and subtract. Now if I run this, this is what we're expecting. Let me zoom in. So I'm going over the lines here a little bit. Zoom out one. Perfect. So we've got a let statement with the name of foo, and the initial value is going to be a binary expression. On the left hand side, we're going to have 1 plus 2, which is right because we see that before the minus. So this has greater binding power because it comes first, or because the binding power is exactly the same for these two. It doesn't matter what order you do them in. Right, 2 minus 3 would be minus 1. If we plus 1 onto that, it's 0. 1 plus 2 is 3. Minus 3 is 0, so it doesn't matter what order we do those in. So we've got a binary expression where the left-hand side is 1 plus 2. The operator is the subtract operator. And on the right-hand side, we have another binary expression. And the left-hand side is 3 times 4, and the right-hand side is 5. Again, because 3 times 4 is 12, 12 over 5. If you did 4 over 5 is 0.8, 3 times 0.8 is going to be about the same, or it would be the same because the binding power is exactly the same. You know, if you times a fraction by a whole number, you just times the tops together and the bottoms. I mean, basic maths, but that is the same as saying, sorry, that should be times. That's the same as saying 3 over 1, which is 3, times 4 over 5, and you just times the top and the bottom together, so you get 12 over 5. So it literally doesn't make a difference what order you do these operations in, or it does make a difference what order, but it doesn't matter whether you do the 3 times the 4 first or the 4 over the 5 first. It makes no difference. So I think we've got basic numeric expressions being passed out, which is great. Yeah, so I'm gonna leave it there. I'm gonna commit this. So I'll say feature pass out basic binary expressions. Sign that. Push it up. Let's go back to GitHub. Let's create the pull request. Better Lexa and parser. And this pull request implements a better API for the Lexa, including next and peak methods. There is also a very simple parser for parsing out binary expressions. Let's merge this in. So this is going into main. We'll delete the branch. We'll check out main. Perfect. We'll do a cargo run again just to make sure. And everything was changed. Do I need to go a get pull? Sorry, get fetch, get pull, get pull. There we go. So now if I run cargo, we're getting exactly the same as before, which is great. We made good progress. Considering we've only spent, 2.5 hours on this project so far, we've already got a Lexa and a basic parser for binary expressions. So I'm going to leave it there for today. Thank you for watching, whether that be live or after the fact. Appreciate it. And yeah, I'll probably do some more in the week. It's been fun working on this project. So yeah, let me know if you've got any questions on Twitter, and I'll catch you next time. Cheers.